All right, let's start. Do you have any questions? Can you hear my voice now? Is there?
Yeah, I can hear you now.
Okay. Yeah, there was some connection issue. Thank you. Sorry, I didn't notice the chat. Everything's good? All right, sorry. Cool. So yeah, I mean, if there's still an issue, now I can see the chat, so you can just type in the chat. Okay, so yeah, to recap, right? We were discussing, so we're recapping, right, the content of 4.4. So there are three concepts: the long-term proportion of time spent at a state, the stationary distribution, which basically is a left eigenvector, right, of the matrix P with eigenvalue 1. And the third, right, is the limiting distribution, which is limit, well, let's call it pi I as well, right, which is a limit as t goes to infinity, probability xt equals to I. Okay. So notice that in at least, right, in all three concepts right here, none of them is guaranteed to exist. Right? Limit is not guaranteed to exist. This is not guaranteed in the sense that it doesn't have to be non-zero. And again, limit doesn't have to exist here, right? So the two, and you know, and agreed, right, and equal, right? So basically, we call all of them pi's for the obvious reason that we want to investigate, right, the case when they're the same. But in general, they might as well be different things, right? Who knows? So the two results that will connect, right, these three concepts are as follows. So theorem 1 says that if the Markov chain is irreducible and positive recurrent, then the long-term proportion exists. Actually, right, it's going to be positive, which will be equals to 1 over expectation of tau I, where tau I, right, is going to be the first time that the chain revisits, right? Tau I is the first time that the chain revisits state I, right? Starting at I. Okay. And of course, right, the whole point about being positive recurrent is that expectation of tau I is finite, right? So, but not only that, the long-term proportion will also be the stationary distribution. Conversely, or not conversely, but on the other hand, if the only solution, if there is no solution. So, okay. Right. I guess here, it will also satisfy this, right? So because it's positive, that's why automatically the sum is 1, right? If there is no solution, right? So let's call this equation star. Again, right? The solution means that you have to have the sum to be equal to 1, because there's always a solution, right? Zero solution here. Only zero solution. Then the chain is either transient or no recurrent. And so basically, right, what theorem 1 gives you is the connection between the first and second item, right? So the first and second item right here is connected via theorem 1. Okay. And basically, if you want to use theorem 1, then when you have a Markov chain, check that the Markov chain is irreducible, which is easy, right? Basically, check that you can always go from one state to another state. And then you investigate the equation or try to solve. Try to solve this, which means you can basically skip this step, right? Because looking at the expectation of tau I is not an easy thing to do. So when you just have a transition matrix and you try to solve this equation, try to find the left eigenvalue, then again, this may or may not be easy to do though, right? As you see with the hotel problem example that we'll go over today, this might be hard, but nevertheless, it's still going to be most of the time easier than investigating expectation of the first return time. Okay, and then from here you can draw the conclusion about the long-term proportion. So basically, what happens is that you kind of, right? So this is called the stationary distribution. So try to find the stationary distribution and use it to draw a conclusion about the long-term proportion. That's the use of theorem 1. Theorem 2, on the other hand, connects item 2 and item 3, right? It says that if a Markov chain is ergodic, which basically is the first 2 items, right? But also non-periodic. Irreducible, positive recurrent, and aperiodic. So basically, right, I mean, here you also already have the connection between the first 2 items, right? So ergodic Markov chain is the Markov chain that has everything, right? Has all 3 items going for it. But of course, the focus here is the second item. Then the limiting distribution also exists. n equals the stationary distribution, and let's say n satisfies. Okay. What else? Yeah, in this case, right, it's just automatically being true and trivial. I guess these two are the same. This limit exists and equals this is the same as the transition matrix if you raise it to the t power and take the limit, it will be the same row, right, of the stationary distributions. Okay. Well, the use of theorem 2 is obvious, right? It's about this limiting distribution. Now, just so you can clarify, right, the difference between these two results, you can see so first of all, right, this is theorem 2. I mean, technically speaking, right, theorem 2 also have this part, but it's sort of, the condition of theorem 1, right? So to see the difference between theorem 1 and theorem 2, you want to look at a Markov chain that is periodic, which is this Markov chain. Okay. Now notice, first of all, for example, does this one have a stationary distribution? The answer actually is yes, right? It does have a stationary distribution. What is it? Let's see, right? If you have pi 1, pi 2 times 0, 1, 1, 0, right? Well, first row, first column, will give you pi 2 and pi 1, right? Therefore, the stationary distribution is 1/2, 1/2. Right? Stationary distribution is 1/2. Okay. Now, what's the long-term proportion of time spent in each of the state? Here you can see, right, regardless of how you start, I mean, you can start at state 0 and state 1, right? The sequence will always be something like this. If you start state 0, then it will be, right? It will not deviate from 0, 1, 0, 1, 0, 1, 0, 1. Therefore, it will spend half of the time in state 0, right? And half the time in state 1. So a long-term proportion of time spent will be 1/2 and 1/2, which you see is exactly this. And of course, right, this guy is positive recurrent and irreducible. Right? What it is not is it's not aperiodic, or it is periodic, right? So what it is periodic. So basically, if you look at the probability of xt equals to, let's say, 1, and you take the limit as t goes to infinity, this does not exist. Why it does not exist? The reason, right, is because, for even t, this will be 0. And for odd t, this will be 1. I mean, it depends on how you start, but you get the picture, right? Basically, for certain values of t, this is impossible, and for certain values of t, is possible. Therefore, in terms of limit concept in real analysis, this won't exist. Okay. Now, most of the time, right, you don't have to worry about theorem 2, in the sense that most of the chain that's given will be periodic, so will be aperiodic, right? So most of the time, it's really about checking these two conditions. Periodicity is automatically given. So that's why theorem 2 is sort of like there in the background, but it's you won't see the distinction as much. I mean, by most of the time, I mean in this class, in the problems you'll be solving. All right, so before we do the problems, right, I want to kind of look at the ideas of the proof, right, one last time to show you, right, why theorem 1 and 2 are true. Right. So the first thing, right, is to establish that the limit exists, the long-term proportion exists, okay, if this is true. So theorem 1 has two portions, right? So for theorem 1, it first established that the long-term proportion exists. And here, right, it's kind of easy to see why, because when you think about it, right, basically, if you look at the Markov chain, right, it starts somewhere, and then it takes some time to go back to I. This is, so let's say it started at J, right? Then the first time is called tau Ji. The first time it takes to go from J to I. And then it spends some time, goes back to I. Spend some other time, goes back to I, right? And so you see, each of these is an independent copies of tau I. The fact, right, that they're copies of tau I is not strange, because you go from I to I, you go from I to I, right? It's the same P, same transition matrix. That's why it's the same tau I. But why are they independent? Remember, right, when you speak of Markov chain, right, things are not independent. Things are usually, things are not independent. Things are usually dependent, right? But here, basically, tau I, like let's say the second one versus the first one, they are separated by the return to I. So this is the Markov property right here for you, that the future and the past are independent given the present. So basically, if you go back to I and then you continue, then your action, right, on the second trip, let's say, is independent of the action of first trip. So that's why they're independent. But, you know, on the other hand, if you kind of look at this picture going to infinity, right, you will see that, well, what's the proportion of time you spend at I, right? So you see in between, of course, you visit other states, but the highlight, let's say, of the trip is when you go back to I. But you see, right, clearly, for every tau I, you got one I, correct? For every tau I, you get one I. For every length of tau I, you get one I. So it's kind of intuitive that the proportion of time you spend at I is 1 over expectation of tau I, where expectation, of course, gives the average length of tau I, right? Does that make sense, right? Let's say for on average, suppose for every 2 years you have an earthquake, then clearly the proportion of time you have earthquake is a half a year, right? Per earthquake, right? So that's exactly what it is. I mean, we're appealing to something like Poisson process here, but it's exactly the same kind of idea, right? So but if you want to use if you want a rigorous proof, then the proof, right, is a clever so notice that the natural definition of pi I is, right, the number of visits defined this way. So basically you count, right, the number of visits up to time n and divide by n, right? But it's a clever way of looking at things by exactly, so notice this is a fixed time horizon, right? The proof will actually look at this picture directly and say that no, what I want to do is I want to look at the number of, let me see, right? So the proportion of time, so it's going to be limit. So let's say this is not what we'll be looking at, but it will be limit as n goes to infinity of the number of visits divided by how long it take to get there, right? And then plus tau ij. Does that make sense? Right? You take the number of visits divided by how long it takes to get there. Sorry, tau gi. Then you get exactly the proportion of time, right? That you visit. Okay. Now again, notice that already here it has the taste of 1 over the average, right? Because you take a number of visits divided by the time, you get sort of like 1 over the average time of visits. And that's what it is, right? Because if you divide both sides by n, sorry, both top and bottom by n, so you got tau ji divided by n plus the sum right? So here tau ik refers to the independent copies, right? Where this is the first visit, second visits, third visit, etc. Right? Or technically speaking, this is the second visit, right? Time between the first and second visit, whatever. And then here, because they are independent copies, law of large number will allow you to say that this is 1 over expectation of tau. Okay. So the long-term proportion exists exactly because of law of large number. Okay, and therefore, this kind of results are extensions of law of large number to Markov chain. On the other hand, right, the law of large number, sorry, the existence, sorry, the fact that the long-term proportion is also a stationary distribution, right? It's the second content of theorem 1, right? Long-term proportions will be equal to the stationary distribution. Okay. And so the idea here is really about this, right? So instead of, so the key idea here to show that the long-term proportion is equal to stationary distribution, the key idea here is to look at the proportion of time let's say of seeing say ij together as a pair in the in the history of the Markov chain, right? Proportion of times seeing, let's say ij. What does this mean? This is the proportion of times that you are at state I, and then immediately, right, make the transition to state j on the next step. This will be pi I pij, right? But you need to kind of prove this somehow, right? Like maybe based on this part, right? Because again, just like anything else, right? This proportion of times is a limit, right? And why does it have to be equal to this? And so you see, this is the limit, let's say as t goes to infinity, of the indicator function that xt equals to I, xt plus 1 equals to j, right? Sum from, let's say, 0 to n, and take 1 over n. And we claim that is equal to pi I pij. All right. But if you can do that, if that's true, then this will be automatically satisfied. Why so, right? Suppose that if this is you can show this, then this is automatically satisfied. Why? Because, right, the proportion of time right, seeing I, right, seeing state I will be, or visiting, right? Seeing is really about visiting. I mean, is kind of, you can call this visiting as well, right? Visiting I and j together, if you will, right? So I and j consecutively, right? So this will be, of course, a sum, a proportion of times visiting I and j, sum of all j. Agree? That's just logic, right? The proportion of time visiting I is a proportion of time visiting ij, right? For all j, sum it up. Correct? Because from I, we must go to some j. But if we establish that this is pi I, and we also establish this is pi I pij, then that's that, which is exactly pi is equal to p, pi times p. And the fact that these guys are positive is from this part. Do we understand? So now, well, let's see here, right? How do you show this? How do you show? So the textbook, right, would seem to say that this is obvious, and well, that's one way to do that, right? Basically, you could say that if you know this is pi I, that's the harder thing, right? Then this is going to be pi I pij, right? Let me try to think. So I want to see if this triggers proof here I want to offer you. One thing that comes to mind, okay, I'm not saying that this is the easiest way, is you can investigate, right, the Markov chain that tracks two states together, two steps together, right, of the X. You can devise a Markov chain Y t is xt plus 1, if you will, right? And then look at like the proportion of time, right, yt spends in state ij, and claim that is this. Anyway, I think maybe let's not spend too much time on this technical part, but I just want to say that this is not immediately obvious, given, let's say that all you know is this limit exists, okay? So you still need something more than that. But let's continue. So for theorem 2, right, what you need, right, is the fact, right, that the limit as t goes to infinity of probability xt equals to I exists. N equal, right, pi I. Pi I being, the long-term proportion, which is also the stationary distribution, right? Because remember, theorem 2 includes theorem 1, right, as part of its condition. So why would theorem 2 be true? So here's the way you can think about it. Basically, theorem 1, right, already gives you that this limit exists, right? Again, this is 1 over n, some indicative function xt equals to I from t from 0 to n, right? Exists equals to pi I. Now, notice that one thing we can do with this is a random sum, right? A random average. One thing you can do with it is take expectation, right? Let's just say for finite n, if you take the average, if you take the expectation, what do you get? If you take expectation of this, you will get 1 over n sum of probability, right? Xt equals to I. Agree? And so suppose somehow that you can switch limit and expectation, and that's some condition for that. But if you can switch limit and expectation, right? So clearly, if you take limit as t goes to infinity here, limit as n goes to infinity here, right? Will be, of course, limit as n goes to infinity of this average. And right now, we do not know if this average exists, because it's the average of sum of probability xt equals to I, right? But if you can switch limit and the sum and expectation, under some condition, right, then this becomes pi I, right? This limits become pi I, expectation of pi I, just pi I. So first of all, right, if you could switch limit and sum, then you know this limit exists and equals to pi I. So now, right, pay attention. This is what? This is just basically a sum of, right, a bunch of, it's a sequence in T, right, of a bunch of numbers. Now, so here, right, it's sort of something like this. If you have the average of a sequence AI, I from, let's say, 1 to n, 1 over n, right? So if you take the average of a series, and somehow is equal to a number, then I'm just saying intuitively, okay? Intuitively, under some condition, it looks like the sequence itself, the terms, will converge to the same value. Intuitively. All right. Of course, not always true. What if those of you who have taken real analysis, actually it's the other way. It's this implication. That's sort of like what you will usually prove, that if the terms converge to a value, that the series will converge to the same value. But you can imagine that the converse is also true. If the series converge to a value, then the terms itself converge to that value eventually, under some condition. And that condition is exactly the aperiodicity. That's all you need, right? Basically, you need these terms to not behave in a very weird way. All right. And so if that's true, then meaning that basically I think you need limit of AI exists, whatever, then you have that. So if under those conditions, you can see, right, that this series, you can conclude that the limit as t goes to infinity all right, that's what it is. Any question? So coincidentally, this may also give you a proof of this identity if you take expectation, right? Because if you take expectation here, you bring inside, you get probability xt equals to I, xt plus 1 equals to j. And that, will be pi pij. But notice that that's not really the proof of this, because this doesn't require ergodicity. It only requires long-term proportion. So anyway, right? So those are the sort of the theoretical discussion of theorem 1 and 2. Like I said, right, majority of the time you're required to interpret theorem 1 and 2 in terms of different situations. You're not really asked to prove stuff. Okay, so let's do problems now to demonstrate that part, meaning that we just show how you use theorem 1 and 2 rather than, to prove stuff with it. Okay, any question? All right, so let's take a look at the hotel problem. Right, as we mentioned last time. So the hotel problem. So the number of guests, let's say the number of, let's say, new guests arriving at a hotel is Poisson lambda, right? Each day. So each day, there's an additional Poisson lambda, right? Number of guests coming to the hotel. And notice that, right, that this can be, I don't know, 0 guests, right? Because a Poisson can be 0 new guests coming in. Now, each guest independently stays, right, at the hotel for a geometric P, right, number of days, and independent of any other guests, right? Let xn or xt be the number of guests at the hotel on day t, right? So A is xt a Markov chain? If so, what is this transition probability? Right. B, find the long-term proportion. So of course, B must be based on, you know, I guess A also entails, is it irreducible, right? And B would entail question about A, right? Meaning that if A is true, then we can ask about B. But if A is not true, then forget about B, right? Find the long-term proportion. That, X, spends at time t I, right? Meaning that find the long-term proportion of days that the hotel have I guesses, right? For any I that's available to the state space. All right, so let's take a look. Well, so is it a Markov chain? So remember, right, a Markov chain really is about, can you determine the transition, right, from one state to another purely based on, right, the previous condition? Well, can we here? If we know, right, that there I guess on day t, is it possible to see or to calculate the probability that there are j guesses on the next day? So the answer is what? Well, first of all, right, the number of guesses on day t plus 1 must be the number of the arrival, right, at the departure, right? So here, a t plus 1 is the number of arrivals on day t plus 1, right? And d is the number of departures. Agree? Then if this is true, then that's that. And notice, right, the number of departure on day t plus 1 would directly depend on how many you have on day I. All right? And that's why it's kind of conditioned. But that sort of already gives you that, yes, it's a Markov chain because this is independent, right, of the previous guess. Every day, there's a Poisson lambda. So AT plus 1 here is Poisson lambda. In fact, right, NAT, AT is Poisson lambda. But DT plus 1, right, I guess here, let us say this condition, right? So AT plus 1 is actually independent of XT. All right, but let's just put it there. On the other hand, dt plus 1 given xt equals to I, right? If they're I guesses at the hotel, right, on day I. Then let's take a look, right? How many guests will be there on day T plus 1? You see, each guest independently stays for a geometric number of days. What does that really mean? It tells us, right, that basically each day, each guest flip a coin, right? If it's head, if it's P, they will leave. Correct? Because P is a success. So they will, P is a success, which is the number, is the event, is the last event, right? If it's a head, they will leave. If it's tail, meaning it's not a success, they will stay, right? So they will stay each day. They will flip a coin. They will stay with probability 1 minus P. They will leave the probability P. Agree? In other words, condition on I guesses. This will be a binomial, IP. And, whoops. And these guys are independent. The arrivals and the departures are independent. All right. And there you have it. Because now you can write down, right, what is the probability that the Poisson lambda minus binomial equals to J minus I. We'll leave that aside, right? Give me a moment. My AirPod is out of charge. Let me get another one. Okay. My screen sharing is paused. All right. Everything okay? I mean, if you can't hear my voice, please type in the chat. All right. So where were we? Right. So basically, now all you have to do is just to write down the the convolution, right, of a Poisson and a binomial. I mean, it's really a Poisson and a negative, right, of a binomial. It's not a negative binomial, it's subtracting binomial, but right, it's just sum, right? It's sort of boring sum. We will leave that aside, right? See a textbook for exact expression. But is that okay? Basically, this analysis shows us that yes, it's a Markov chain. Okay. Any question? All right. Well, now, is it irreducible? So, well, what does irreducibility mean? Irreducibility means, okay, so first of all, right, then what are the state space of xt? xt can have, right, anything from 0, 1, 2, etc., right? Basically, you can have 0 guests at hotel on any day, and you can have any number of guesses, right? Why? Because the Poisson lambda, right, can accommodate any number, and the geometric, right? Basically, each guess, right? Basically, here, all I guesses, right, can leave. That's a positive, right, probability there. So, but from on the state space, is it possible to go from any state I to any state j? Meaning, right, that, well, you look at this, right, meaning that is there some combination of I, A and D that gives you j minus I, right, for any I and j? Well, the answer is what? Seems yes, right? So why? Because, for example, let's say if j is bigger than equal to I, if you want to go from I into a more guests next day, one possibility, right, is to let the arrival takes care of it and let the departure be 0, which is a positive probability, right? And if this is less than I, then one possibility is let the arrival be 0, which is a positive probability, and let the departure, which is now I minus j, right, because you're subtracting it, take care of it, right? So there you go. That's why the chain is irreducible, because you can always go from one state to another. Okay, so far? So now, let's look at the long-term proportion. So, you know what I think, right? Here, I want to show you actually the meaning of this. So maybe let's try to look at the exact expression a little bit. How do we find the Pij here exactly? So Pij here, right, will be basically such that the Poisson lambda minus the binomial I is equal to j minus I, right? So, and they're independent. So basically, right, it will be all combinations of the Poisson lambda and binomial I, right? That will give you, so for example, let's see, right? Here's one thought. If the Poisson, so if the binomial I, right, is takes value k for some k, right? Then the Poisson lambda must take value what? J minus I plus k. Agree? And here you just have to sum over all legal k, right? And it's really the legal case here that we need to think about. First of all, right, k cannot take on any arbitrary values, but it must go from 0 up to I, right? That's the most. But is that really the range of k? The answer is no, because here, right, this guy by definition of a Poisson must be non-negative. right? So therefore, K must be at least J minus I if J minus I is positive. Sorry, sorry, this guy must be at least non-negative. So the lower bound of K, right, must be so that this guy is non-negative, right? So we have to look at something like that. So basically, let's call it LB, right? And let's call this UB, lower bound, upper bound. Lower bound will be the minimum between 0 and I minus J. Okay. You understand? Because, right, if I minus J, the number of, right, today minus tomorrow, if this is positive, right, that means there you want less guests tomorrow, right, than today. Then the departure, right, so the values of the number of departure can be 0, right? Because, wait, am I right? If I minus J is positive, sorry, it's a max, sorry, not a min. It's a max, right? Yeah, if right, yeah, if I minus J is positive, that means there are less guests today, right, than yesterday. So of course the number of departure cannot be 0. It has to start from that, right, and move on. So that's a lower bound, right? What about the upper bound? Can K goes all the way to I? Let's see here, right? Can you have a maximum number of departure being I? Well, I guess the answer is yes here, right? Because you have I guess you can have K departures, that's fine, right? But the minimum number of departures will depend on the relationship between J and I, right? If J is bigger than I, the minimum number of departure can be 0. But if J is less than I, the minimum number of departure must be at least J minus I, right? Any question? All right, so now what I want, the reason why I write this down is I want to show you that basically for question B, find the long-term proportion, right? Theorem 1 tells you to just try to solve for pi p equals to pi, right? Sum of pi I equals to 1. That's always, right, what theorem 1 tells you, right? To find the long-term proportion, look at that. We have already checked that it's irreducible, right? So let's just try to solve for that. And unfortunately, right, that may not be very practical in real life. For example, with this Pij, try to solve for pi p equals to pi numerically would probably be a nightmare. Okay. So, of course, trying to investigate the first time the chain returns to state I is definitely not even on the table. So the question is, can we have an easier way to solve this? Is this the point of this problem? And so here's upper bound, right, is I. The answer is yes, because you don't have to solve it exactly. So for part B, right, solve. What you can do is you can just guess an appropriate pi. And then check that it works. Why? Because you're relying on the fact that pi is unique. Pi being unique. Okay. If this is unique, then as long as you find one that works, that must be it. And uniqueness comes from where? Uniqueness comes from uniqueness of the limit, right? It's being a limit, it's unique. So sometimes, right? And this might sound bizarre because how do you even guess the eigenvector, right, of a matrix? Well, this is where it gets interesting, because notice that what we're given is really not a matrix. I mean, it is, right? It's an infinite matrix. But what we're given is a structure of arrival and departure, right? We just write this down from the convolution of the arrival and departure. So if you sort of somehow try to accommodate this arrival and departure and not really thinking about stationary distribution, I mean, not thinking of the equation, then actually this is an easier way to solve it than focusing on the equation. That's what I'm trying to say, right? So what can we do here? So the key here, right? The key here is to guess the form, well, guess an appropriate pi, right? What it means now is to guess the form of pi. And basically you can guess that pi, the stationary distribution, so is a Poisson lambda. Well, lambda 0 to distinguish it from the Poisson lambda, right, of the arrival. All right, why do you guess this? So first of all, right, the state space is 0, 1, 2, etc., right? So you need to find a distribution on this state space. Well, how many distribution you know lives there? Not many, right? Poisson, uh, geometric, and negative binomial. But more importantly, right, what does Poisson have going on for it? Poisson has two things going on for it. Poisson plus Poisson is Poisson, right? Independent. Sum of independent Poisson is Poisson. So remember, right, pi here represents the distribution of number of guests on the AI, right? So what you're saying is if xt is Poisson lambda 0, you want to somehow conclude that xt plus 1 still is Poisson lambda 0. That's what it means to be stationary, right? And notice xt plus 1 is xt plus at plus 1 minus et plus 1, right? Right. And so xt plus 1, wait, what do I want to say here? Yeah, so if xt is Poisson lambda 0, right? And at is Poisson lambda. So I'm just explaining the sort of the intuition on why we can guess this way. Then you see that the sum here is a Poisson. And so it sort of preserves the Poisson structure. What about the departure? Condition on xt is a binomial, right? But unconditioned on xt, meaning if xt is a Poisson, remember, then this is about, right, the yoga, right, studio problem, where if guests arrive at a yoga studio according to Poisson lambda, and it with probability p, a guest is a male, probability 1 minus p, a guest is a female, then the number of male arriving at the yoga studio is a Poisson lambda times p, right? Meaning if you select a portion of a Poisson lambda, then that's also a Poisson lambda p. All right. So that's exactly what allows us to say that this is Poisson lambda 0 times p. All right. And if you combine these three together, right? So you want to say that this is Poisson lambda 0. Okay. And you see you have an equation going on for you, right? Basically, which means the rate here is lambda 0 plus lambda plus, sorry. I hope I'm right. So this is basically lambda 0 times 1 minus p, right, plus lambda 0. Well, I guess these two cancel, right? I'm being silly. So basically you got lambda 0 times p is equal to lambda, or lambda 0 is lambda over p. So there's a solution there. And because of this equation, it shows you that if you have a, so the stationary distribution is Poisson lambda p, lambda over p. So pi I, right, the long-term proportion will be e to minus lambda over p raised to the I over I factorial. That's the long-term proportion. Any question? So, right, this problem sort of demonstrates, right, the analysis of pi p equals to pi, but not directly, let's say, right, but using a guess and check. I have to say, right, who knows how many times you have to pull this trick, but it's a option that's worth remembering when we solve this problem. Any question? All right. So if not, let us look at some other questions. So second question here will be question number 20, right, in your homework. which says a transition matrix P is doubly stochastic, right? That's a term. Doubly stochastic if sum over I Pij goes to 1 for Oj. All right. So what does this mean? Remember, right? A transition matrix P automatically have, right, that you sum over all the rows, you get 1, right? Fix an I, fix a row entry, sum across it, you get 1. So here, if you fix a J, meaning you fix a column, then you sum over the row. So you sum over a fixed column, right? You sum over the rows of the fixed column, you will get 1, right? So, yeah, all right. So that's what it is. So basically, that's why it's called doubly stochastic, because you sum over columns or you sum over the rows, you always get 1 either way, right? Of course, a trivial doubly stochastic matrix is a matrix with all constant entries, because, right, but that it doesn't have to, right? It doesn't have to be. For example, you can have something like, who knows, 1/3, 2/3, 2/3, 1/3, right? Again, many. But if you have a doubly stochastic matrix, transition matrix and a Markov chain at that, then says that if, right, xt is irreducible, because you don't know if the structure of the matrix is enough to give you irreducibility, but if it's irreducible and consists of m+1 states, zero to m, show that the long-term proportion is given by pi j, which is 1 over m+1. Sorry, pi j. You can call it pi I, who knows? So first of all, what's the message here? The message here is that a doubly stochastic matrix has a very simple stationary distribution. What is it? Uniform, right? Discrete uniform. So how do we prove this? There's also another subtle message here, right? Which I'll explain. What's another subtle message? Another subtle message is that here M must be what? Finite, right? Well, it shows right here. Why? I mean, or not, who knows? Doesn't matter. But what is a doubly stochastic matrix that we know? I mean, doubly stochastic, right? The, random walk, right? The one-dimensional random walk. Because for a one-dimensional random walk, what happens? If you're at state 0, then you will have, right? You will go to state -1, right? and 1 with probability P and 1 minus P, right? So every chain will have something like this going on every row, right? So this is a row I, and this is I minus 1 column, I plus 1. But then the next one will have what? 0 here, 1 minus P, P, right? The next one will have 1 minus P. You see, right? So exactly, you will have a P entries, right, on each. So it's sum to 1 on the row, sum to 1 on the column, right? But as we know, the random walk, right, infinite, the one-dimensional random walk is either transient if P is not 1/2, or it's no recurrent, right, if P equals 1/2. But I guess that sort of doesn't contradict this, right? Because 1 over this, when m equals infinity, is equal to 0. But if you want a proper distribution, then m must be finite, right? So how do we solve this? Well, here, right, it's just really a direct application of theorem 1, because you just have to show, and again, right, a guess, you see? That also demonstrates about the guess. Because again, if someone magically gives you a guess, all you have to do is check it. If it works, then it works. There's only one solution. Meaning, right, you check that it's the stationary distribution. Because if there's a stationary distribution, then it will be the long-term proportion, as long as the chain is recurrent. Sorry, as long as the chain is irreducible. That's what theorem 1 gives you, right? And so let's see. So if is it true that pi p equals to pi? For pi being you know, constant. Well, pi p, right? So 1 over m plus 1. Right, pi, remember this equation says what? Pi I, pij, right? Sum over I is equal to pi I. But you see, this exactly is a column sum on the P. And the answer is yes, right? Because this sum is that's it. Any question? So just in case you think that this is like a special thing, right? Who knows how often you are into a doubly stochastic matrix? Let's take a look at this. So this is question number 26. It says that this is a shuffling approach.
Could you just scroll a little bit up, Professor?
Yeah. Okay. So this is a shuffling approach. Not shuffling. Shuffling. Ouch. Shuffle. So they're N cards, okay? It's a deck of N cards. Here you can, yeah, they allow for any N, but you can just think of like 52 cards, right? Deck, our regular cards. So basically, you choose, right, number I randomly from 1 up to N, okay? So basically, it's a uniform choice. And then you take the card in position I and put on top. All right, so that's one move, right? You choose a number I randomly, uniformly, and then you choose card I and put on top, and then repeat this. So in the limit, the deck is perfectly shuffled. That is any n factorial ordering is equally likely. All right. So first of all, right, what object are they asking for here? Are they asking for the long-term proportion? No, right? They're not. They're asking for the limiting distribution, right? Because that's actually right there, right? In the limit. So basically, what are they saying? And so basically, first of all, what is this Markov chain? What is the state space here that we're looking at? What is this Markov chain tracking? The Markov chain is tracking the ordering, right, of the N cards. So basically, how well shuffled, right, is the deck. So basically N factorial, right, the N factorial possible orderings of the card, right? So notice, right, the move is a transition, right, from one ordering to another. When you choose a card I and you put it on top, you have move, right? You have moved from one ordering to another. Okay. And so one thing that's interesting here, of course, is what's the transition matrix P? What's the size? It will be n factorial by n factorial, which, right, of course, is huge, right? And so again, of course, lurking in the background somewhere is pi p equals to pi, right? The stationary distribution. And of course here, well, we need to check in the process that the chain is irreducible, meaning you can go from any ordering to any other ordering, maybe in so many steps, right? And then you also want to check that it's aperiodic, because this is about the limiting distribution, right? It's not about long-term proportion. Because you see, long-term proportion, I just want you to distinguish the concepts here, right? The long-term proportion won't make sense here, or at least in terms of shuffling, you can say, who cares about the long-term proportion, right? Because you want to say that as you shuffle, at any moment, or after you shuffle for a while, the deck at that moment is well shuffled. You don't want to say that, well, on average, I have passed through all the orderings, whatever that means, right? Because for the shuffling of the deck, you want to say that, yes, right now, when you're looking at my deck, it's well shuffled. Of course, in the limit means t goes to infinity, you'd say you have shuffled 1,000 times or whatever, right? It's not long-term proportion, then that's the concept here when it comes to shuffling the card. It's a limiting distribution. On the other hand, right, I don't know, something like the hotel problem, right? Probably the long-term proportion is a relevant question, who knows? But right here, definitely limiting distribution is a relevant question. So irreducibility and aperiodicity. Again, it's probably so easy to skip over these and just try to look at that. But, right, because that's the main point anyway, but still, right, these guys must be investigated, right? The second thing you see is, right, even though pi p equals to pi seems like an easy thing to solve in theory, in practice, you have to be very careful. Because, well, if even for n equals to 10, I think it's hard to visualize a 10 factorial by 10 factorial matrix, right? Let alone something like 52. So it's along those lines where you have to, again, you look at this equation, but indirectly somehow, right? So that's the theme of this question. Any question? All right, so let's take a look at the irreducibility. Is this Markov chain irreducible? Can we go from any ordering to any ordering using this approach? Well, the answer is yes, right? It's a bit painful to explain it in details, but again, remember, irreducible, right, just means that you can go from any state to any state. Doesn't matter how many steps, and doesn't matter how small the probability, as long as it's a positive probability, right? So what happens here? What happens here is that, right, the move, right? Basically, what is a transition matrix? The transition matrix basically change one, right? So, for example, suppose right now, so let's call it, right, x1, x2, etc. up to x sub n, right? Where x sub n is the nth card, right? You know, basically, x1 can be the second card, this can be the fourth card, this might as well be the third card, right? the move will move the ith card into, right, the first card, right, first position. So it will move from here to xi, x1, x2, xi minus 1, xi plus 1, right, xn, right? That's the move, right? And so, of course, the move allows you to move any I though, because you choose I uniformly. So if we just talk about possibility, that it's possible to move any, right, including you can choose x1, right? If you choose x1, then actually the x stays the same, right? You can choose any x, any card, and then move it on top. But it will change the ordering, right, like that, one card at a time, correct? But you can kind of see then, right? Then because you can change one card at a time, like that, you can literally design the moves from one any ordering to any ordering with a very let's say in n steps or whatever, very time consuming, right? You change it one card at a time to move in the right position. Each of each of them will take you a probability of 1 over n. So maybe the total probability is 1 over n squared, whatever. But right, it's small but it's non-zero. And so, right, you just move one card at a time until you move one from one ordering to another, right? So it's useful. Okay. Again, I mean, if you have to explain it down in writing, okay, but that's what it is, right? What about aperiodic? Is it aperiodic? Well, what is aperiodic? Aperiodic means you can, there's no, how to say this, right? There's no regular gap, right, between move from I to J. All right. So meaning that you're not forbidden, sorry, to return to I, sorry, to return to a state I, right? You're not forbidden to return to state I only after 3 steps or 4 steps or something like that, right? And here you see, right, you can return to state I after 1 step. So clearly it's aperiodic. Okay. So both of these are good. So all we have to focus on now is solving this. But like I said, right, notice that it's a bunch of argument that seems like to state the obvious, whatever, but it's not, right? You have to really look into it to make sure that the details are there. But now let's focus on the main point. How do we solve this? Pi p equals to I pi. So that notice that limiting distribution is my voice okay, or can anyone hear me okay or not? Sorry, I just logged back in because my internet seems to be unstable. Can everyone hear me all right?
Yeah, we can hear.
Okay, was there like a disconnection at some point or not?
Yeah, there was just now.
Oh, okay. Yeah, all right, because I somehow I thought that, yeah, I just want to make sure. Thank you, appreciate it. A moment here. Let's just do this. All right. So if I do it this way, I won't be able to see a chat, but it's just all right. So where was I, right? So what I'm saying is that when you investigate, right, this equation pi p equals pi, right, you need to, well, it's not easy to solve because you have n factorial, right, number of states. But on the other hand, if you notice, the suggestion is that the number of ordering is equally likely, right? In other words, it's a uniform distribution. And what kind of uniform distribution do we know? Or what kind of transition matrix do we know has uniform distribution? The uniform distribution is here, right? So in other words, again, right, this is kind of ad hoc, but because it's suggested that the limiting distribution is uniform, right? We will try to show that P is doubly stochastic. Now, let me say why. First of all, right, there are several things that's hard if you want to really write down P in details. The first thing is the size of P, right? The first thing is the size, but the second is that notice what do you want to be state 0, state 1, state 2, etc. Right? Because it's the number of orderings. So if you really want to write down in details, you have to say, okay, this is my first order, this is my second order. And that's painful to even assign, right? An order to order, whatever. So in the abstract, if you just show that whatever P you write down is doubly stochastic, you're good, right? Rather than you have to really provide the P in details. So this is yet another lesson on solving, right? Solving for the equation indirectly, okay? Without naming the P or looking at the equation super closely. So how do you show that P is doubly stochastic? To show that P is doubly stochastic, remember, right? You have to show that P I j sum over any I is equal to 1. Sorry, sum over I for any j. What is Pij? Pij is probability xt plus 1 equals to j condition xt equals to I. Right? Meaning that you move from I to J, right? And the sum over Pij, sum over all the rows, doesn't have a probabilistic meaning. But basically, it says that for a fixed state J, where you can go into it. Okay. Now, if you look at the shuffling, right? So basically, it's sort of the opposite of this picture, right? This is from I going to J. But it's the opposite where it says for a fixed state J, for a fixed ordering, how can I get into it? And it's a probability of me getting to this fixed state is 1. And you can see, right, this is where it sort of gets obvious because, well, how many ways can I get to an ordering? There are n ways, right? Where, what does that mean? That means that I have to take this x1 here and then move it back, right? Basically, it'll be x2, etc., xn, and the x1 is somewhere in between, including, of course, x1 being right here, right? But if you just basically have the x1 somewhere in between the x2 to xn, including being right at the xn or x2, then by the way of shuffling, right, you will move to the j. And each of these, of course, is a 1 over n probability. So yes, right, the sum over Pij, I from 1 to n is equal to 1. Here, sum over all I, right? But so sorry, I should say that sum over Pij, sum over all I, but you can show that exactly n, right, entries, each with probability 1 over value 1 over n. Namely, the ones where the x1, right, is moved back. And so this matrix is doubly stochastic, therefore automatically by the previous problem, the n factorial ordering is equal to likely. Any question? Okay. So let us now continue with the next one. It's quiz 4. And this is question number 22. So, which is also another application of doubly stochastic matrix, right? Let Yn be the sum of n independent rows of a fair die. Fair dies. Find the limiting probability that Yn is a multiple of 13. All right, and here the textbook says that you define an appropriate Markov chain and use, right, the doubly stochastic matrix. Okay. So the first thing to notice here is what? The first thing to notice here is that Yn itself is a Markov chain. Do you see that? Why? Because Yn itself is a random walk. I mean, it's not the random walk that we think about, but it's a random walk that only walks to the right, right? Because it's a sum of the fair dice. So what roughly it says, suppose you're at a position, right? Then at each state, you move to the right, you know, into I plus 1, I plus 6, right? With probably 1/6 each. So you keep moving to the right, right? But the position of the next step only depends on the position of previous step. Therefore, it's a Markov chain. However, right, using that Markov chain to try to find, right, clearly this is a limiting distribution, is not appropriate. Why not? The first thing that you notice right away is what? Yn is not irreducible. And then Yn is clearly transient. Right? Because it only keeps going to the right. It never goes back. Right? It never goes back. But it doesn't matter, right? Because that's not what we're really interested in when we investigate the question of multiple of 13. So what are we looking at? What's the Markov chain that we want? The Markov chain that we want must be irreducible and must somehow be recurrent, right? I mean, the point is we will prove that it's recurrent too, but you know, but what is it? So if you think carefully about it, right, that's the only thing that's not, that requires some work here, that Xn will be Yn mod 13, right? Basically, you just really want to look at Yn mod 13. So the state space of Xn is 0, 1, up to 12, right? Where 0 is the state you are interested in. So basically, you're trying to look at the limiting distribution of Xn equals to 0, right? And so you try to establish that one, Xn is irreducible, and Xn is not periodic, which, right, is easy on both. Because, right, how do you go from, let's say, a state to another? You can just find two sums, right, that gets you there, right? Say, for example, to go from 1 to 12, you just need a sum of 5 and a 6, right? Which has probably 1/6 each. Oh, sorry. Yeah, right, 0 to 12, right? Okay. And so, and why is it aperiodic? It's aperiodic because you can go from a state to a state. Are you forbidden to go any numbers? You could, basically you can go from 1 to 1, right? Yeah, because 13, right? 13 is prime, right? Because 13 is prime. That's why there's no, and 13 is a prime. That's why there's no forbidden steps where you can go back, right? From a state to a state. So aperiodic here because 13 is a prime. That's what it is, right? If you have something else, you might have a periodicity built in, right? Notice that 13 here is not innocent. if you have like something like 4, then you might have periodicity built in if you mod 4. Okay. But then, right here, you can write down the transition matrix of X, right? Well, from one state, where can you go? So Pij will be what? So from one state, right, you can only go to clearly 6 other states, right? So 1/6, right? If j equals to I plus, I don't know, sorry, k mod 6, right? Sorry, mod 13, k equals 1 to 6. And then 0 otherwise, right? But if you look at this matrix, right, and you look at the columns of it, let's say you look at the column I, right? Let's just, so for the sake of discussion, let's say you look at column 4. Okay. So you look at, let's say P41, P40, P41, etc., up to P46, right? Sorry, P412. Notice that it's exactly because of mod arithmetic, right? So j equals to I plus 1, meaning I is equal to j minus k. Sorry, j is I plus k, therefore I is j minus k, right? You see that there are exactly also 6 entries here that are different by 6, by a number between 1 and 6, right? For example, right? So again, so if you look at Pij or fixed j, that means you look at the number of i's that's possible to go into j, right? Again, if you try to investigate sum of Pij equals to 1, then you try to fix a j and you look at all i's, Pij is positive. But here, right, to go from I to j, you must somehow be able to add a k to it. But clearly there are only 6 possibilities, because clearly, like, j equals I plus k, meaning I is j minus k, mod 13. Therefore, for any columns here, there are 6 possibilities. We probably want 6 each. Therefore, right, all in all, the answer here will be 1/13, right? Because it's a uniform distribution. Any question? All right, so I think it's a good place to stop here. All right, so let's continue on Friday.